Hi, welcome back to the class on modeling. Today we are going to talk a little bit more about vector spaces. I told you that this would be important. No? So vector spaces is what we are going to talk about, and today we are going to talk about what is meant by a dot product. You're thinking, I know what a dot product is, but we want to generalize it to all kinds of vector spaces. No, dot product cannot be used What I mean by that when I say it cannot be completely general is not all vector spaces you can define dot products. It may not make any sense. Even though the vector space sense, that is, I can do algebra, scaling and adding and things like that, but I may not be able to do a dot product. Okay, so if I can do it, then you can actually do quite a bit more geometry. So this is related to geometry, and the idea is very simple. In 3D or 4D or something like that, we know what to do, right? If I have vector v, which is ABC, and then vector W, which is MNO, then V dotted with W is AM plus BN plus CO. Okay, so this is our typical dot product. There is nothing which prevents us from talking about a weighted dot product. So that means given, so V dotted with W with a weight rho will be called rho 1 AM plus rho 2 BN plus rho 3 CO. So these are the weights. It's possible. So for example, I could do 3 AM plus 2 BN plus 1 CO, something like that. I can do that, right? That's also a dot product, except that it weighs all the terms differently, and it's possible. Okay, now for functions, so if I want to write it in general, I'm going to write as V as V1, V2, V3, and then W as W1, W2, W3. Then V dotted with W will be sigma I equal to 1 to 3 V1 W1, sorry, Vi Wi. You with me? And of course, I don't have to do 3. I can do a column vector with 20 elements, and I can do dot product. And in fact, in many cases, we do that, especially, for example, when you're computing grades. I have columns and columns of all your different exams, and then I weigh them differently, and then I take an average, right? Averaging and things like that have closely related with dot products. Okay, so now what I want to be able to do is generalize this to functions. So I want to be able to do the following thing. If I'm given a function f, another function g, what is their dot product? The answer is f dotted with g will be defined. This is just a definition. It's integral. Notice the summation has become an integral. F of x, g of x, dx. You're with me? So for example, if f of x is x squared and g of x is x cubed, and they're all between x lying between 0 and 1, then f dot g integral 0 to 1 x squared times x cubed dx, which is integral 0 to 1 x to the 5 dx, which is x to the 6 over 6, 0 to 1 which is 1 over 6. That's the dot product. Okay, and of course, two vectors are said to be orthogonal if their dot product is 0. Okay, for example, if I do from minus infinity to infinity sine m pi x over L, sorry 0, let's redo 0 to L, times sine n pi x over L dx between 0 and L, it turns out to be 0 if m is not equal to n. That means this function f of x and this function g of x are perpendicular. Okay, and now we come to the core idea. This is called the fundamental lemma of variational calculus. It's important. It says if f of x is continuous function and integral of f of x h of x dx is equal to 0 for any h, then f of x equal to 0. So what it says is that if a function is continuous and it is perpendicular to every function we know, then that function has to be 0. Okay, this is very useful. You will see this. Okay, and it looks like common sense, and you're wondering why it should be continuous, because I could have some bizarre stuff. You know, for example, I can have f of x equal to 0 for x not equal to 0 and equal to f of x equal to 50,000 for x equal to 0. Okay, then its integral with respect to all other functions will be 0, right? But this is not a continuous function, you know what I mean? So this is where, so what happens is typically there will be some pathological cases, and we want to avoid the pathological cases by saying that the function is nice. That is, if it is high at one point, around it should be high, something like that, you know what I mean? It has to be continuous, otherwise you'll have all kinds of difficulties. You can weaken the continuity requirement quite a bit by demanding that we can talk about something which is called 0 almost everywhere, and you can really get technical. But this is not a course in mathematics, and we will be kind of sloppy about it because we don't know enough to be completely correct. Okay, so we will be kind of sloppy about it, but we will always be concerned about the fact that there could be pathological cases, and we will have to worry about them. Okay, so that's the second thing. Okay, so now we have talked about what is meant by orthogonality, and of course you can have orthogonal with respect to a weight. What it means is that integral f of x g of x rho of x dx equal to 0. So this rho of x dx is the weight, and usually the technical name for weight, not surprisingly, is called measure. So it says orthogonal with respect to a measure rho, okay, or density rho. Sometimes we will use this, and in fact this is quite useful, for example, there are all these classes of special functions, you know what I'm talking about, like for example sinusoids. Sinusoids are orthogonal to each other, okay, and they form the basis of Fourier series, right? And you know that, right? So then the next one are Bessel functions and other things which are not orthogonal to each other directly, but they are orthogonal with respect to a weight. And orthogonal functions are useful, especially if they form what is called a complete set. So orthogonal functions are useful. If they form a complete set. What I mean by complete set is every function should be representable by them. That is, any function f of x can be written as summation ci, let us write it as pi of x. And these things are called orthogonal. So this is actually the equivalent of using Cartesian coordinates. Right? So if I have, if in a three-dimensional space, if I have e1, e2, e3, they are orthogonal, right? They are actually even better. They are orthonormal. That means that they are also unit lengths. Okay. Here, I mean, we don't really need the unit length, but we need the orthogonality condition for things to work out very easily. Then, we can write any vector in terms of the basis vector. So these are basis functions. Turns out to be very useful. Finite element methods, for example, use basis functions that are not completely orthogonal, but most of them are orthogonal. Because, see, for example, a function that is here, like that, is always orthogonal to a function that is here. If f1 is like this and f2 is like that, then f1 times f2, or f1 dotted with f2 will be automatically 0. Right? So functions which have local support, that means they are only 0 over a finite small region of space, they are very nice functions because it's easy to do orthogonal. Okay, so those kinds of things you will see, so finite element methods, any kind of approximation scheme, most of them rely upon orthogonal functions to keep our problems reasonably simple. We'll see that in fact even for probability, there are these things which are called polynomial chaos expansions, where again we'll see this orthogonal function show up. So all kinds of things, I mean, nice things happen with orthogonal functions. Okay, but I want you to understand that this idea of doing analogy from ordinary vector space into functions is very, very useful. But functions are a bit more pathological than ordinary vectors, so you have to be careful. Okay, so this is as far as orthonormal or orthogonality of functions and inner product goes. Now we can talk about what is meant by magnitude or norm of a function. Is, in our case, this particular thing is called the L2 norm, which is integral minus infinity to infinity of f of x squared. Or you can write it as f of x, f dotted with f, take the square root of this. Sorry. You can generalize this in many ways. For example, there is these things which are called the p norms, LP. Will look like integral f magnitude of f of x to the power p dx to the 1 over p. Okay, so this L2 norm works beautifully with dot product. LP norms, if p is not equal to 1, will not work with dot product. Okay, and interestingly enough, there is a peculiar feature about this. So let us say I put p equal to 1000. Okay, what does a L1000 norm look like? equals integral f of x to the 1000 dx to the power 1 over 1000, right? Notice what happens here. You know, the places where f of x is maximum will contribute a lot. So the places where f of x is pretty small will not contribute anything, but places where f of x is maximum will contribute a lot. The higher the value of p, the more contribution from the region where f of x is large. In fact, if I do L infinity, this is called the max norm. This is a very simple one which says max over x of f of x. And you can prove this. This is difficult to prove, but you can get the idea. Okay, we will typically be using something like this. We will have occasional need for a norm like this. This norm is very nice because it works with dot products. This norm does not work with dot products. Okay, but it has its own use many times. Okay, so we are always interested in creating nice vector functions or nice vector spaces where you can figure out how big a vector is, which is a norm. We need to be able to figure out whether two vectors are perpendicular to each other and things like that. So that the really useful place is this L2. Okay, but we will see later that many times even LP is quite useful. Okay, so now that we have all of these things, we are going to stop here, and our next lesson is going to be talking about maxima and minima.